Okay guys, good morning everyone. Today we'll be looking at lighting. Okay, so this is sort of, I've sort of jiggled around the order in which we're covering things, just so I could cover Bezier curves, because some of you required that for your assignments. So what we're going to do is look at lighting today. Okay. There aren't going to be any of those activities I normally do. It's very difficult to do it with lighting. Lots of sort of niggly calculations. It's more, these lighting models have been already inbuilt into MATLAB and other graphics libraries, and it's quite difficult to actually do a example calculation. So there won't be any sort of activities as such. Okay, so today we're going to be looking at lighting. Okay, and why should we look at lighting? Why is lighting important? Well, in a 3D environment, if you're modeling a 3D environment in the virtual world, without lighting, you have no clue as to depth. Okay, so here I've got the teapot, which remember is the Utah teapot, or often known as Newell's teapot. Okay, and what I've done is, believe it or not, this plot on the left, that is a plot of a 3D teapot. Okay, so I've loaded up the values, I've applied the Bezier patches, I've plotted it in 3 dimensions, and I've plotted it in red. But without any lighting, because I've removed all of the edges from the polygons, it just looks like a silhouette. Okay, it just looks like a flat red blob. Okay, there's no clues as to the shape of the object. But the one on the right is exactly the same. That's exactly the same plot as this one, except I've added a lighting model to it. So immediately you can see we've got a clue as to the sort of the shape of this object. So we've got the darkened sort of shadowy areas on the right, the lighter areas on the left. So the light for this plot is coming from over here, somewhere on the left. Okay, so that's why we're doing it. Fairly, so almost fairly obvious need to have some form of lighting model. And light, it comes in one of 2 different types of model. And the first we're going to look at is the idea of a direct illumination. So here we've got our light source. Okay, so a light source, the light from a light source falls on a surface, an object, and then the light goes to your eye. So everything you're looking at, you're not actually looking at the object. You're looking at light reflected off of the object. Okay, so that's what we call direct illumination. So for example, one of these lights here in the ceiling falls on any surface you can see around you, and it goes into your eye. That's direct lighting or direct reflection. The other type is when we have light bouncing off of other objects. Okay, so in this case, in the second case, the light source here, light falls on an object and then it's bounced off of another object and it goes into the viewer. Okay, so this is what we call indirect illumination. So direct illumination is where it just falls on the object straight to your eye, and indirect is where light bounces off of other objects and then goes to your eye. In real life, both direct and indirect illumination is what you can see. Okay. Now, from a mathematical point of view, it's very expensive, or very computationally expensive, to actually deal with the indirect illumination. Okay, so direct lighting models, and that's what we're considering today. Okay, we don't really, there are models which take into account the bounce around of light, but we won't consider those. We're only considered direct lighting models. So direct lighting models only considers light that falls on an object and goes straight to your eye. Okay, it does not take into account the light bouncing around. Okay. And the model we're going to be looking at today is one called Fong's reflection model. Okay, this is the sort of the most common model. There are other types of models, okay, global illumination models. This considers light that reflects off multiple surfaces in addition to the direct illumination. Okay. For example, ray tracing you may have heard of. So that's when what you do is you send rays out from the camera to every object in your scene, and then you work out where the reflected rays will hit, and you keep doing it until it falls on a light source. Okay. Now, global lighting models, these are very expensive to calculate. So these tend to be used for when you're pre-rendering something. So, for example, if you think of the Pixar films or any computer graphics films, they would use a global lighting model because it doesn't matter how long it takes. They've got supercomputers, they'll run their models, and it doesn't matter if it takes sort of 6 months to render their movie, because once they've got the movie, that's fine. In something like a computer game, you haven't got that time. Okay, computer games, often 30 or 60 frames a second, you're having to do all your calculations on the fly. Okay, so that's why computer games mainly use, I say, lighting models. There are modern techniques where you have a sort of semi-global lighting model in a computer game, but traditionally they tend to only use direct lighting. It's quicker. Okay, so we'll be looking at a Fong's reflection model. Okay, named after, don't know how to pronounce it, it's a Vietnamese name, Bui Chuan Phong. Okay, he was actually at Utah as well with Yule, so with the teapot. So in the early 70s, University of Utah were fairly prolific in the graphics research. Okay, and it's a direct lighting model, which is, as I said, used on the fly. So it will calculate the lighting quite quickly. And what it does is there are four sort of sub-models which are combined to give us Fong's model. Okay. So we have models for what we call ambient lighting, and don't worry, I'll be defining what each one of these means in a minute. So we have a model for ambient lighting, a model for what we call diffuse reflection, a model for specular reflection, and finally an attenuation. Okay, don't worry, I'll explain what each of these means. What each model has is quite a few variables, and we'll go through them in a minute. By setting these variables at different values, we can determine what the lighting properties should be of our surface. So, for example, you may want a shiny surface in your virtual world. So if you want a shiny surface, you'll set the variables so that the reflection model or the lighting model will give you the appearance of a shiny surface. Alternatively, you might want a dull surface. For example, this carpet here, it's fairly dull. Not dull as in boring, I mean, well, it's grey, it is boring, but I mean dull as in the reflection of the light off of it makes it look like a rough or a dull surface. Okay, so this is Fong's reflection model. And I'm going to go ahead and just explain what each of the subparts of the model are. Okay, the first one is ambient reflection. Now I'm going to try a little experiment here. Oh, that's the wrong button. Okay, we've got really complicated lights here. Oh no. Oh, there we go. Ah. And oh. Okay. Not quite. If I stand in front, I'm going to need to block this light off. What I'm trying to do is block off all light sources in this room. Obviously, we've got some light still coming in. But what you'll realise is, as you turn off all the light sources in a room, eventually you'll start to notice your eyes will get used to sort of the objects in the room. So unless you've got absolutely totally pitch black, you should be able to make out some outlines of objects. And this is because of ambient reflection. What's happening is tiny bits of light are bouncing around everywhere. So if I was to try to turn out those lights again, I couldn't get rid of all light sources. So what light source you do have would bounce off of objects, and you get your night vision, and you'll be able to make out various edges. And this is because light bounces around everywhere. Now this is ambient reflection. How do we model this mathematically? Well, Fong assumes a very, very simple model of ambient reflection. All we have is this model here. Now A is the amount of reflection, okay, and it's equal to IA. Now this is a value which is the intensity of the ambient light, multiplied by Ka, which is called the ambient light coefficient. All you do is you just set those values to whatever you want. Okay, so IA, I for intensity, A for ambient, and Ka is just like a sort of tuning thing. Okay, so if you've got your virtual world, you'll set your IA, and then if it's sort of like you want it at night time, you'll set Ka close to 0. Then that will be very dark. If you're on a very bright scene, you set Ka to be 1. Okay, so what I've done here is I've plotted our teapot, and I've chosen different values of Ka. That's the ambient light coefficient. So when it's quite low, anything less than sort of a quarter, and you probably wouldn't make out the teapot. You can see you can barely make it out. Notice there's no other. I haven't included any other type of reflection here. It's just purely ambient. Okay, and as I increase the Ka coefficient, you can see it gets brighter and brighter and brighter. Okay, and finally, Ka equals 1. That blue color is the color of the actual object. Okay, so ambient light, all that does is sort of turns lights on and off, or sort of makes your scene lighter or darker. Very, very simple model. One thing you notice about this ambient light as well, it's given us no clues as to the shape of this teapot. All it's done is make it brighter or darker. Okay, so ambient light is independent upon any light source. Okay, so that's the ambient model. The next model we're going to be looking at is the diffuse model. Okay, and diffuse reflection is essentially reflection of light off of rough surfaces. Okay, so here we have a surface. I've tried to draw a rough surface. Imagine that's sort of, I don't know, gravel or a carpet or something like that. Okay. What we have is we have these incident rays. So our light source is up here somewhere, and we have parallel rays of light. So if a light source is far enough away from our surface, the lights will be parallel. Okay, so imagine, for example, the sun is far away from us to assume that we have parallel incident rays. So as these rays of light hit the surface, they'll be scattered. They'll be scattered in all sorts of directions. Okay, that's our model. Well, that's our diffuse reflection, and we need a mathematical model of this phenomena. And what Fong decided on is the amount of light which is reflected using diffuse reflection is based upon the angle. You can see here there's an angle theta, okay, between the normal vector to a surface and the light vector. Now the light vector is a vector going from the surface to the light source. Fong suggested L for the label of the lighting vector, which is obvious. Okay, so these blue vectors, that's showing that the light is scattered equally in all directions. Okay, so the blue vectors are your light being scattered. So when our light source, or the angle between the light source vector L and the normal vector is small, we have lots of light being reflected off of the surface. But as I increase that angle theta, okay, so as the light, the angle between the light source and normal vector becomes greater, what we have is we have a reduction in the light which is being reflected. So down here, the angle is large, almost 90 degrees, okay, and therefore we have less light being reflected. And until, if our light source is, the angle between the light source vector and the normal vector is 90 degrees or more, we'll have zero light being reflected. If it's more than 90, our light source is behind our surface, and therefore no light rays from the light source will actually hit the surface. Okay, so that's a diffuse reflection. So it's all about this angle theta. Okay, the smaller the angle theta, the more light is reflected. Okay, so how do we describe that mathematically? Well, this is the Folds model. Okay, D stands for diffuse reflection. That's the amount of light which is reflected by diffuse reflection. And here we have a couple of variables. IP, or I, is intensity, and P means point light source. Now, a point light source is, for example, any of these bulbs in the ceiling. It could be the sun, anything which emits a light. So that's the intensity. So you might have, for example, in your virtual world, you might have a candle with very small intensity. You might have the sun with very large intensity. KD is similar to Ka in the fact it's a diffuse coefficient. Now this is like a tuning thing. Imagine you've got a equalizer on your music. Okay, you move it up or down depending on how much diffuse reflection you want. Okay, and that's in the range 0 to 1. And theta is the angle between the light vector and the surface normal. Okay, we've got a little max calculation here because cos theta can be 0. Okay, when the angle is greater than 90 degrees, cos will be 0. You can't have 0 light being reflected, so we have a max. So that it's always either 0, it's always going to be positive. Okay, but I mentioned before the reason we're using a direct lighting model is because it's efficient, or it's more efficient. Unfortunately, here we've got a cosine calculation, which is quite tricky for a computer to do. So we can get rid of that cosine calculation using our old friend dot products. Okay, so just to remind you, this will be very familiar to you by now. Two vectors A and B. Theta is the angle between those two vectors, and that's related to the dot product using this relation here. It should be sort of ingrained into your brains by now. Okay, so A dot B is equal to the magnitude of A times magnitude of B times the cosine of the angle between them. Now, if L and N are unit vectors, okay, what we have is L dot N would equal 1 times 1, which is obviously 1, times the angle between them. So in our diffuse model here, we have this cosine theta, or we can replace that with a simple dot product. Okay, so cosine is an expensive calculation, so we always ensure that your lighting vector is a unit vector, as is the normal, and then that's quite an easy calculation. And here's the teapot with the diffuse reflection. So it's not too easy to see from where you are. Okay, this is KD. This was a number between 0 and 1. This is kind of like how much diffuse reflection you want to apply. So when KD is small, you can barely see the teapot. Okay. As you increase KD, you increase the amount of teapot you can see. Okay, and this is a combination of ambient and diffuse. If ambient wasn't there, the teapot would be invisible. So you've got to have some ambient light to actually see the teapot. And here you can see diffuse, and you can start to see we have the shadowing. So the light source is somewhere on the right. Okay, so when the angle from the light source hits the surface, When that angle is small, the angle between the light source and the normal vector, you have lots of light being reflected. But as we come around to this side of the teapot, the angle is larger. Sorry, yeah, the angle gets larger, so it's come less and less until we're right on the left-hand side, where the angle is either 90 or more, and we have zero reflection. Okay, so that gives us our diffuse reflection, and we can tell the shape of the teapot. We can tell it has a lid, and we can tell it's sort of a rounded shape. Okay, so that's diffuse reflection. One thing you notice, it looks dull. Okay, the surface of that teapot looks dull. It's not shiny at all. So the next thing we're looking at would be the idea of specular reflection. Anybody know where that is? I nicked it off the internet just this morning. Don't recognise that. Yeah, Salford. Anybody been to the Media City or Salford Keys? Yeah, that's Salford Keys. And the reason I nicked it is because I wanted a picture of some water. Now this, as you can see, the water here is reflecting all of the light above. And this is an example of specular reflection. Okay. Anything shiny is specular. For example, a mirror, that's almost 100% specular reflection. Now, specular reflection is a reflection of light off of shiny objects. Now, if an object is shiny, what it means is its surface is very smooth. Okay, so as our incident rays come in and hit the surface, they'll all bounce off as parallel lines. Okay, so all bounce off in the same direction. So whereas if I go back to the diffuse model, way back here, you can see the bouncing off a rough surface scatters the reflected vectors all over the place. Go forward now. Specular reflection, light bouncing off of the smooth, shiny surface. It's all in the same or similar direction. Okay, so mathematically speaking, we need to add or introduce two new vectors to our model. So again, you've got this as a surface. Again, you've got the light source, and the light source vector goes from the surface to the light source, and you've got the normal vector. And again, you have the angle between the light source and normal. What you also have is a reflection vector. So any light which hits the surface is reflected off at the same angle as it hits it, angle of incidence. Okay. And we also have V. Now V is a viewing vector. Now that is where the viewer is in relation to the surface. Now the viewing vector is needed because we're not always going to be bang on the reflection vector. So, and alpha is a difference, is the angle between the viewing vector and the reflection vector. Now the closer the viewing vector is to R, i.e. the smaller the angle alpha is, the more of the reflection you're going to see. Okay. The further away the viewing vector is, i.e. the larger the angle alpha, the less of those reflected rays you're going to see. Okay, so this is Fong's specular model. Okay, so S the specular, and we have IP, which is the same IP as the diffuse reflection. So that's the intensity of the point light source. So you may have a really, really strong light, and therefore IP is large, or you may have a really sort of dim light, like this candle, the IP would be small. Your KS, which is the specular coefficient, and like KA and KD, this is in the range 0 to 1. Okay, so how much of the specular, how much shininess do you want in your object? N is something we call a specular exponent, and I'll explain that on the next slide. Okay. And alpha is the angle between R and V, and you can see we have cosine alpha to the power n. Okay, and this cosine alpha to the power n, that determines the amount of light that is reflected. So what you do is you set n to be when you're designing your object, or you want, okay, I want this surface to have this shininess, that's what you set N to be. Having a look at this Spectre exponent, okay, what we have here is I've graphed, here's the angle alpha on the bottom, and this is cosine to the power n. So when n is equal to 1, we have this blue line. Okay. As we increase our Specular exponent, what we do is we narrow the band of cos to the power n. So for example, the red line is n equals 5, black line n equals 50. Okay. Why is that needed? Well, that gives you some control over the shininess of your object. And here I've got the same plot as before, but this time I've turned off ambient light and I've turned off diffuse light. So this is exactly the same teapot as before. As you can see, all we're getting is these like white patches. Notice we're not getting the blue. This teapot is blue, but we're not getting any of the blue. The specular reflection only gives you the light, which is the same colour as the point light source. So here I've assumed that the point light source is white, so the specular only reflects white back at you. Okay, so similar to a mirror. What colour is a mirror? You can't tell, because all the mirror does is reflect any light which falls on it. Okay, so what I've done here is, this is the ambient light, and here we've got specular reflection. Here we've got specular exponent of 50. So here, 50 gives us a very narrow band, and you can see we've got very narrow sort of reflection off of it. Now, as we decrease the specular exponent, we get more and more light reflecting off it. Okay, so it gives you control of how shiny your object is. So in this case, using a specular exponent of 1 is probably a bit too much. Okay, maybe 5 is better. Okay. But notice, even though it gives clues to the shape of the object, it doesn't give us any idea what the colour of the object is. The specular reflection only reflects the light the same colour as a point light source. Okay, just going back to this diagram here. Here we've got the reflected ray. Okay. We need to calculate that, and I know we did something similar in assignment 2, but just in case you've forgotten, I'll just revisit this. So to calculate the reflection vector, we need the idea of vector projection. So again, I've gone back to my old friend, the dot product. Okay, so here I've got the vectors A and B, and what I want to do is I want to project vector A onto vector B. Okay, so vector C is kind of like the shadow of A onto B. Now, to calculate C, what I do is, here we have the dotted line makes a right angle triangle. Okay, and the length of C can be determined using the cosine ratio. Okay, so if that's the adjacent side, that's going to be the hypotenuse, and we know the angle between them. Okay, so using definition of a dot product as before. Okay, well, cos theta, cos is adjacent over hypotenuse. So the adjacent side is the length of vector C. Hypotenuse is the length of vector A. Okay, so I can replace the cosine with magnitude of C over magnitude of A, but you can see that magnitude of A is just going to cancel out with that A there. So we've got magnitude of B times magnitude of C. Okay. Rearrange that, it allows me to calculate how long the vector C is given the vectors A and B. Okay. So A dot B over the magnitude of B. What if B had a magnitude of 1, i.e. if it's a unit vector, we get rid of that denominator and we can say the length of C is equal to A times the unit vector B. Did I say B? Unit vector B. Okay, so this gives us a length of the vector C. Now, if B is a unit vector, all we have to do is to multiply the length of C by the unit vector B to give us the vector C. Okay. So this is a projection. This is vector projection. So if I know what A is, I can work out what the unit vector B is, and that C is a vector A projected onto B. Okay. Why have I just taught you that, or just gone through that? Well, it's used in calculating a reflection vector. Okay, so here I've got a surface, and I've got a normal vector pointing perpendicularly away from the surface. Okay, there's my light source vector. There's my reflection vector. Okay, I know what L is, and I know what N is. I don't know what R is. Now, what I can do is I can pick up. Oh, sorry, before I get to there. Okay, so what I've done here is I've projected L onto the normal vector, and that gives me this vector here. Okay, so L dot N multiplied by N. Remember, we always assume that L and N are unit vectors. Okay, well, I picked up R, and if I put R on the end of L, I get this vector here, which is the same as two lots of the projection of L onto N. Okay, so L plus R is the same as 2 times the projection of L onto N. Okay. Rearrange that, that gives you the reflection vector. Now, when you did the collisions assignment, quite often L is switched. Now, in lighting models, I've done it this way because that's the way Fong wrote it in his original paper. Quite often, L is going towards the surface. In that case, you just multiply that by -1, and it'll be L minus 2 lots of L dot N times N. Okay, so if you often see it in a different form, that's just because this vector here is often switched around. You just multiply it by -1, get the same thing. Okay, so that's how to calculate reflection vector. Notice it's all dot products. Dot products are very easy to calculate. Okay, so all we do now is we have, I've got attenuation then. Okay, so far we've got ambient, which is how bright or dark your scene is. We've got diffuse, which is reflection off of a rough surface, and specular, which is reflection off of a shiny surface. The final thing we need is attenuation. This is loss of light energy over space. So the further away you get from a light source, you'd expect it to go dimmer. Okay, so loss of light energy over space. Basically, we have this variable FATT, and that's just a variable which is multiplied by your diffuse and your specular components. In physics, theoretically, it should follow the inverse square law. So if d is the distance from your light source, FATT should be 1 over d squared. But in practice, what happens there is your scene becomes far too dark. Okay, so in Fong's lighting model, we use this equation. R is some radius. So once you're past R, you can't see that light source, and that light source doesn't apply. So there's some ratio between the distance and R. Square it, subtract it from 1, that gives you your attenuation factor. That'll be a number between 0 and 1. Okay, so if you've got like a candle in your scene, the further away you get from the candle, the less light from that candle will fall on your object. Until you get so far, further than R, and then no light will fall from that candle. Okay, so that's just attenuation. So the further away you get from a light source, the less light will fall on it. Okay, so we've got ambient, we've got diffuse, we've got specular, we've got attenuation. We can combine all those, and this is the Fong's reflection model. I is just how much light's reflected. It's just intensity. Okay, so remember your ambient light, IA and KA, that's just up or down. No sort of nothing special about it. It's just how light you want your scene. So if you've got let's say you've got a nighttime scene, you might have KA being low, and therefore it's dark. So that's easy. Diffuse, this was a diffuse reflection. Here I've multiplied it by FATT. So remember this is a number between 0 and 1. Okay, so that will dim if it's far, if your object is far away from the light source, that will dim it. And there's your specular. If you notice here, both diffuse and specular use the same FATT and IP. So you can actually factorize that if you want. I have it in this case here. Okay, and notice it's all about, instead of cosines, we have these dot products. Now this is for a single light source. So in your virtual world, if you've got one light source, that's what you'd use. If you've got multiple light sources, now just looking around this room, you've got 1, 2, 3, 4, 5. You've got 15 lights in the ceiling. You've got light coming from the doors. You've got light coming from the projector. Okay. What you do is you calculate it for each light source. So you calculate this for each light source. Now the ambient light is the same. It doesn't matter what light source you've got. All we do is we sum the diffuse and specular for each separate light source. Okay, so we've got the sum. We've got M, in this case, we've got M light sources, attenuation, intensity of each individual light source, and all of these, like the lighting vector and the reflection vector, will be for each individual light source. And if you add them all together, so here we've got the teapot again. Top left is just ambient. Top right, I've got diffuse. Bottom left, I've got specular. If I add them all together, you have your teapot rendered. And it's not perfect, but it gives a good representation of that teapot there. Lots of variables. Okay, I'm not expecting you to get it straight away. Okay, I was about to say I'm not expecting you to remember this, but I'm afraid it could pop up in your example. Okay, so just go through the variables. It's not too difficult to remember them. Remember, I is intensity. Subscript A means ambient light. Subscript P means point light. Okay. Here I've got lambda. Lambda is just your red, green, or blue. So whereas you've got these equations, you'd have to do this each for red, green, and blue. Okay, so you've got 3 for those 3 colours. O is your object colour. Okay, so if you've got, for example, I've got a blue blue teapot here, the diffuse reflection, okay, will give off that. Sorry, the ambient reflection gives you the blue colour. Diffuse and specular just gives you the colour of the point light source. K's are just numbers between 0 and 1, Ka, Kd, Ks. Those are your like tuning sort of variables, so how you want your object to look. N is your spectral exponent, how much light you want reflected off your object. FATT, the loss of light over space. N, L, R, and V, normal, light vector, reflection vector, view vector, respectively. So it's not, even though you've got lots of these, it's not too difficult to remember what they are. Okay, I mentioned at the beginning, but I'm not giving you, well, it's difficult for me to give you an activity based upon this. The reason being is probably fairly obvious. You've got lots of variables, lots of calculations. It's a bit tricky. All of this is already loaded into MATLAB, and in MATLAB, it's got a material command. So if you want to apply lighting to the object in MATLAB, and I'll show you that in the next lecture how to do that. You can specify how what sort of reflection properties the object has by this material command. Now, it's got some preset values. So if you want material shiny, that gives you a shiny object. Material dull, obviously. Okay. If you want to actually set it yourself, you can see you set it by the ambient, diffuse, and specular coefficients, and also, if you really want to, N there. Okay, so you've got some control in MATLAB how it looks. Okay, and that's going on to the next lecture. Okay, so just to recap, Pong's model is a combination of 4 things, 4 submodels: ambient, diffuse, specular, and attenuation. Any questions about that? It's all very theoretical at this sort of stage, I'm afraid. It's not something which I'll get you to apply. But it's one of those things it's useful to know, and it's useful to see how we go from a real world phenomenon, as in lighting, to your mathematical model. No questions? Right, I think I've finished there. No point in me going on to shading. I'll save that for the next lecture. Okay, there is a sign-in sheet going around, so put your name on if you haven't already done so.